Hello, everyone. My name is Sasha Lowen, and today I will be presenting on my research, data-intensive adaptive management in organic agriculture. Yeah, I am a third-year PhD student at Montana State University, and my advisor is Dr. Bruce Maxwell. So just an overview of my presentation. I'll talk a bit about the main methodology of my work, which is something called on-farm precision experimentation. Introduce that as a topic, and then go through a general example with that using a seeding rate experiment of wheat. Then I'll follow that up with some work that we've done with seeding rate experiments on hemp, and then some of the work that we're doing with nitrogen rates, including a blood meal experiment over a field, and some of the work that we're doing with green manure analysis on farmers' fields, and then discuss some of the future work that we're intending to do with our project moving forward. So our primary research question is whether we can use on-farm precision experimentation, which is essentially a collection of precision ag tools to increase farmers' knowledge of their fields and thereby improve their yields and economic returns. So what is on-farm precision experimentation? It is something that is driven by farmer-driven questions. So we work primarily with what is a question that a farmer has, how can they do something with adaptive management. We design field-scale experiments for them to implement and run. And all of these are always done with conventional machinery, that is to say the machinery that the farmer has. And then at the end, we get together and we provide an analysis to try to understand what happened in the experiment over that field. So on-farm precision experimentation, at a glance here, we start over here on the left side with a prescription map and an experimental design. So essentially, we are coming onto the field and varying some input rate across the entire field. And that can be any input that the farmer has control over. In conventional agriculture, my lab mate Paul Hegedus works with farmers to vary synthetic nitrogen rates. My project is only with organic farmers, and so we are primarily working with seeding rate variation. So for example, we could vary our seeding rate across the field randomly in order to try to understand how those varied seeding rates will affect the yield at the end of the day. We then go through this middle process here where we try to acquire as much data as we possibly can from the field, including remotely sensed data from satellites, so NDVI information from previous years, the current growing year, topographical information, including elevation, aspect, slope, and so on to try to understand the variation in the field. We then collect weather data, the as-applied map, so what actually was put down by, for instance, the seeder. And once the crop is up and grown, we collect yield monitor data off of the combine, and then economic data because we want to make this, the output from this model, a economic net return. We then run through our analysis. I'll show you some examples of some multiple linear regression analyses that we've done, as well as some nonlinear GAM analysis. And from that, we come up with a optimized net return. So from that analysis and from the varied input rates we put across the field and the data that we've acquired, we come up with a new prescription map that would be the optimized prescription for seeding rate in this example for that field. And we suggest that that will then be our optimized seeding rate for the following year that this crop is planted. And the cycle continues, and we can continue to learn about the field over time as we keep this experiment going. So we have a number of experiments set up across the Northern Great Plains, including 4 farmers working with us here in Montana. And I am from Southeast Manitoba, and so my farm there is conducting some of these experiments as well. So I'm going to start by showing you an example of a wheat seeding rate experiment that we conducted in Manitoba. So we begin with an as-applied map. So here is a 170 acre field in Southeast Manitoba. And you can see here we put in 3 different seeding rates across the field, across the entire field to try to understand what that variation would do. We then go through and collect as much information as we can. Here you see a field elevation map with blue being low and red being high across the field. We collect NDVI information. So this is a satellite metric that allows us to track how green an area is. So you can see the relative strength of a previous oat crop on this field from this information. The as applied map, as I mentioned, goes into the model as well. And then once the crop is up, we collect this yield map off of the combine, which allows us to see how those different seeding rates were um, uh, ended up conducting themselves in yields across the field. And you can see that the data is quite messy, but we try to get through that with our analysis. And then because we want to know what the net return for the farmer is, we can include previous or our best idea of what the the product return on wheat in this case would be for an organic wheat product. So here's our analysis from that field. So this looks pretty messy. Each of these black dots represents a yield point spread across this graph in terms of elevation. So along the x-axis, we're seeing our elevation. Along the y-axis, we're seeing our yield. So you can see this data is it looks very messy coming off the combine. But when we run it through our analysis and we see the 3 different seeding rates here in 3 different colors, we can see that there is a difference in how the seeding rates turned up in the yield analysis. So you can see that generally this blue bar, which represents the highest seeding rate, tended to outcompete the other 2 seeding rates. So generally a higher seeding rate was optimum in this field. However, as we increase our elevation, as we get to the higher points in the field, the hilltops and so on, that relationship inverts and we actually see the lowest seeding rate coming out on top. And so there are the higher points on the field, the lower seeding rate is preferred in terms of yield output. So if we put that all together into a model, what we get is, this is our input randomized seeding rates across the entire field. We get these other data sets such as elevation and NDVI, and then a final output of yield, and we come up with a new optimized seeding rate. So this is our map that we generate that says if we planted the optimum seeding rate across the field, what would that new seeding rate look? So the following year, then we suggest that that farmer plant in this optimum seeding rate. But because we've only done 1 year of experimentation, we really don't have a very clear idea of how the year-to-year variation will look like. And so it's key to continue the experimentation. And so we keep randomized strips in the field so that we can keep learning about how that field will vary over time in space. So just to bring that home to an economic analysis, this is the net return in US dollars per hectare. So this is what the experiment the farmer actually made from this seeding rate in that year. If they had applied average rate, which they normally would have done across that entire field, they would have made a significant amount more money actually, approximately $15 to $20 more per hectare. But if we had put in the optimized seeding rate, that is what we predict the farmer could have made if they had been able to put in this perfect or ideal seeding rate from the 1 year of data, they would have made considerably more per hectare. And so we find this is just 1 year of analysis, but our initial analysis shows that this has some promise for economic return for the farmer. Switching gears here a little bit. So that was a wheat experiment that I showed there. The following year, that was 2019. The following year, 2020, we put in a hemp seeding rate experiment. So I know a lot of you know about hemp, and hemp is becoming more and more of a topic here in Montana, where a lot of farmers are interested in growing it. I will point out that this is Manitoba, where we have a considerably different amount of rainfall there. So we expect about 23 inches of precipitation annually. So we typically have too much precipitation across our fields rather than too little. So that's a major difference. But we are very happy with hemp production there. Is a very strong competitor with weeds. You can see this is my friend Matt Ratchford standing in the field. He's about 6 feet tall, so you can see that hemp is towering over him in some places. So we're very happy with the weed control provides. But we also put in this as a hemp, as a on-farm precision experiment using hemp. So you can see we've applied these varied rates across the field with a low rate of 24 pounds per acre all the way up to 40 pounds per acre across that field. And then here is our yield output. So you can see the north half of the field was considerably poorer than the south half of the field, where green is higher rates and red is lower rates. And I haven't done a complete economic net return analysis on this yet, but just running this through a model, you can see that the lower seeding rate here along the x-axis, so this is the 23 approximately seeding rate towards the low end, tended to have a bit of a lower yield. Then as we progress through our seeding rates, we actually do see a slightly higher yield up towards that 45 pounds per acre yield. However, again, this data set is pretty messy, but we do see that upward trend towards a higher seeding rate. And it will be interesting to see once I start the economic analysis to see whether those seeding rates are actually contributing more economic return to the farmer, or whether because of the seed costs, a lower seeding rate might be more beneficial. And then just to show another example of something that we're doing. So here in southeast Montana, in Ekalaka, or near Ekalaka, we have a precision nitrogen experiment with blood meal on wheat. So the farmer here is using prescription blood meal top dress on their spring wheat, and we varied those rates across the field. So just to show you what that looks like. So here is a 300-acre field of spring wheat, and these varied bars represent different levels of blood meal applied. So you can see the white is a 0 application of blood meal, all the way up to 60 pounds per acre of blood meal in relative nitrogen units. And so just so you get a sense of that field there, here's the elevation map again, and you can see the brown is the lower areas, the teal is the higher areas. So you start to get a sense of what that variation is across that field. And then we get to our output from the field, which is of course our yield. And you can start to see where there are good points on the field and some poorer points on the field. And when we run that through an analysis to try to understand how the yield actually functioned as the blood meal was varied, you can take a look at this graph here. So blood meal runs along our x-axis, where we go from 0 to 60 pounds, and yield is along our y-axis, where you can see which yields did better. And just discerning from that by elevation, so the lighter blue line here along the top is the highest elevation, and this darker blue line here along the bottom is the lower elevation. And so you can see generally the higher elevation did better yield-wise, and the lower elevation did poorer yield-wise. However, what's very interesting to see here is that the effect of the blood meal, as we increase in elevation, the blood meal has a greater effect in terms of raising the yield. And in fact, in the low areas, almost seem to have a detrimental effect on the yield. And so if we were to suggest an optimum blood meal application for this field in the future, we would definitely suggest higher rates in the higher elevation and much lower rates in the lower elevation as a prescription. And we're still in the midst of analyzing some of this data, so stay tuned for an economic analysis of all this next year. And then this farmer also has a protein monitor on their combine, so we were able to do a protein analysis as well. And you can see that there are some similarities in the yield and protein, although in some places it seems to be inverted. And when we look at, again here, blood meal along the x-axis, protein along the y-axis, you can see that the higher elevation now is this lighter blue is along the bottom, and the lower elevation line is along the top, suggesting that in the low areas, the protein was the highest, and in the high areas, the protein was the lowest. And what's interesting here is that the blood meal rate generally has a slight increase over application. So once we get up to that 60 pounds per acre, you can see that we generally, our lines are going up, and we are seeing a higher response in protein as we apply more blood meal. And that doesn't really seem to matter which elevation we're at. Generally, more blood meal means more protein across this field. And again, we would like to do further analysis to really dig into what the economic returns on that will be for this farmer. So there's just a summary slide of what we saw. We see our elevation, we see our experimental rates applied across the field randomly, and then an output of yield and protein. So moving forward, we would like to repeat this experiment and see if we can increase yield and protein for the farmer by applying more precise rates of that blood meal in areas where they are more better suited to increase those metrics. So that's a summary of on-farm precision experimentation. We begin with some sort of randomized input across the field. We collect as much data as we possibly can. Again, I should say that all of this data acquisition is free, and that this is data being passively acquired by farm machinery and satellites that is free for a farmer or a researcher to gather. We analyze this collection of data. We produce an optimized net return map for that farmer for the following crop year, in which we recommend applying those optimized rates with continued experimentation, so that every year we learn more about that field, and every year we produce a more precise and accurate map of prescribed rates. So moving forward into the future, we would like to pursue on-farm precision experimentation applications on the 5 farms that we're currently working with. And essentially the only requirement for this project is to have GPS on your tractor and combine, so that we're able to collect and gather yield and applied rates. And so if anyone is interested in participating, feel free to contact me for sure. And some of the other projects that we're working on, I mentioned already blood meal. Using manure in a similar way to vary rates would be very interesting to process. No one is doing that yet, but that would certainly lend itself to this methodology. And something we do have a number of farms working on is, which we think will be very applicable in an organic setting, is varying the rates of their green manure plowdowns, such that we try to optimize the amount of nitrogen present for the following cash crop by varying these green manure plowdowns seeding rates. And so we actually have 3 farmers who have put in varied rates of green manure this year, and next year we will see what the results are from the cereal crop that they plant into that the following year. And just to back up, and we did do a greenhouse experiment where we planted green manures, in this case pea, at varied rates in these different boxes. You can see this is a low rate all the way up to a high rate of pea in each box. We followed that up. We tilled those peas into the soil and allowed them to decompose. And then we planted a kamut cash crop, as an example, into the same boxes to see how the kamut would grow in response to these varied rates of green manure. And we did indeed find that there was an optimum seeding rate for the pea. So you can see this is kamut seeding rate along the x-axis and total grain, or aka yield, along the y-axis. And you can see that we do find an optimum seeding rate, which is a little towards the lower end of what we tried. And that is represented by this green line here. So this green line represents the pea seeding rate that produced the highest follow-up kamut yield. And so following from this first principle, we think that there's definitely an application promise for applying varied seeding rates of green manures to try to optimize that nitrogen for the following cash crop for organic farmers here in Montana. Another interesting part of the project is I have been mapping weeds on a number of these farms. And so we are trying to determine if with the seeding rate, we can both control nitrogen via the green manures, but also if we can try to control weed patches using higher or lower seeding rates across the field. And so here's an example of a farm where you can clearly see weed patches. And so I've been going out there mapping these with drones and GPS to try to see if we can have some control over them with varied application of seeding rates. And then finally, the output of this project, we want to make something usable for farmers. So we have this idea that we should put together an app or some sort of software application that we're very much in the process of making, and that would be workable for a farmer without much research training at all, to be able to conduct some of these experiments and really gain some extra knowledge about their farms and about their operations through this data-intensive management. And that's all I have for today. So thank you to everyone, all of my lab mates, the farmers that work with us, my advisor, Bruce Maxwell, and of course, all of our funding sources. So thank you so much for listening today, and please hit me up with any questions. Thank you.